So we have what is called a density curve. So a density curve is always on or above the horizontal axis. A density curve always has an area of 1 underneath the curve. And a density curve can come in many different shapes. So a density curve describes the overall pattern of a distribution. And the areas under the curve represent the proportion of observations that fall in a particular range. It is also an approximation that is easy to use and often accurate enough for practical use. So we have a histogram there. It is a distribution. So a density curve for this histogram might look something like that, where it is approximating the histogram there. It's not exact, right? Some of the bars are under the curve, some of the bars are over the curve, but it's approximating that distribution. Okay, so I'm gonna go through the next part quickly here. Disadvantages of a density curve. It does not describe outliers. No set of real data is exactly described by the density curve. As you can see in the histogram there, the median of a density curve is the equal areas point, the point that divides the area under the curve in half. And the mean of a density curve is the balance point which the curve would balance if made of solid material. Okay, but for our purposes today, the median and the mean are the same for a symmetric density curve because we're going to look at a special type of distribution called the normal distribution. But first, the notation, okay? So we have the mean and standard deviation. If the data is coming from a sample, then the mean is designated by X bar and the standard deviation is designated by S. If it is coming from the population, then the mean is designated by the Greek letter. Anybody know this? It's mu. It's the Greek letter M for mean. And these are things that you need to know before you go off to college, right? The Greek letter. Had such high hopes there for my third period. They have been dashed yet again. This is sigma. This is a Greek letter M, and this is a Greek letter S, standing for the mean and standard deviation. And so we will get into these differences much more in depth later in the course. But for now, X bar and S come from a sample, and mu and sigma come from a population. Okay, so turn the page from here and let's talk about the normal distribution. There are a lot of different types of distributions that we're going to look at, starting with this one today. It's a fairly important distribution in terms of stats. We use an idealized distribution to model distributions whose pattern is close to that ideal. And the first model we are introduced to is the normal distribution. Okay, you can describe any normal distribution by two numbers, the mean mu and the standard deviation sigma. So a lot of times the shorthand for writing a normal distribution might be this, and then let's say it's 5 and 2.5, where the first number is the mean of that distribution, mu, and the second number is the standard deviation, sigma, which is 2.5. Okay, so any normal distribution is designated by the mean and the standard deviation. And we're going to look at some of the characteristics of a normal distribution. All normal curves have the same overall shape, which is they are symmetric. And they are single peaked. And they are bell-shaped. Any specific normal curve is completely described by giving two things, which is its mean, mu, and standard deviation, which is sigma. The mean is located at the center of the symmetric curve and is the same as the median. Why are those two things the same? Because the distribution is symmetric, right? And the blank controls the spread of a normal curve. That is the standard deviation. Curves with larger standard deviations are more spread out. And so I don't want to spend a whole lot of time on this, but there's a link between statistics and calculus here. If we have a standard if we have a normal distribution that is symmetric, the mean will be at the center, and then the standard deviation will be at the points of inflection. Calculus people, right? What's a point of inflection? When
Change in concavity.
okay, it's where the second derivative is 0 or undefined, and it changes signs. Okay, stats people, don't worry about that. Okay, but what you need to know for our purposes, okay, the larger the standard deviation, the wider the normal distribution will be. The smaller the standard deviation, the narrower the normal distribution would be, and those standard deviations are determined by the change in concavity, the point of inflection there. So this, however, you do need to know. All normal distributions have the properties described by the following rule. Okay, and this is called the empirical rule. And sorry about that. You do need to know this. So the empirical rule says, first of all, this only applies for a normal distribution. It has to be normal for this to apply. But if it is a normal distribution, then 68% of the observations will fall within one standard deviation of the mean. And 95% of the observations fall within 2 standard deviations of the mean. And approximately 99.7% of the observations fall within 3 standard deviations of the mean. Okay, so that means, look up here at this little graph. If I have a standard normal distribution, which we'll talk about in just a second, okay? It's centered here at the mean, and let's say that the mean is 0 and the standard deviation is 1, then 68% of all that data will be within 1 standard deviation of the mean. And 95% will be within 2 standard deviations, and 99.7% will be within 3 standard deviations. And that is if if it is a normal distribution. That must be the case. And there are a lot of things in terms of what we are going to look at in general applications in life that are normally distributed. IQ tests, for example, okay? They write IQ test with a mean of 100, and let's say a standard, I don't know, I'd have to look it up, but let's say it's a standard deviation of 15. Okay? Well, if that's the case, then the empirical rule says that if of all the people that take an IQ test, 68% of them will score within one standard deviation of the mean. So if the mean is 100, then we're saying that 68% of the scores on an IQ test will be between 85 and 115. And 95% will be between 70 and 130. That makes sense? Okay. And so on. Okay, so if you take an IQ test and you score 160 on the IQ test, right? Then you're way, way, way above the mean. Right? You're several standard deviations above the mean. Okay, because the empirical rule says almost all of the observation will fall within 3 standard deviations of the mean. And so something extremely rare would be outside of that. Okay. Questions for me? Anything so far? Well, let's look at an example here. It says, according to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 8 centimeters. Sketch this distribution, labeling the mean and the points 1, 2, and 3 standard deviations from the mean. So let's go ahead and do that. We're going to draw a sketch of a normal distribution. And we have the mean here at the center. And it says the mean is 149 centimeters. And then we're going to go out 1 standard deviation from the mean. So let's say maybe right there and right there. So this would be 1 standard deviation, and this would be -1 standard deviation. And the standard deviation in this case is 8 centimeters. So I'm going to add 8. That gives me 157. And over here, that would be 141. And according to the empirical rule, what's the percentage within 1 standard deviation? 68. And since this is symmetrical, that means that there's going to be 34% between the mean and 1 positive standard deviation, and 34% between the mean and 1 negative standard deviation. And so I'm going to keep going here. Let's go out to 2 sigma, and this would be -2 sigma. And so I'm going to add 8 to 157. That would give me 165 centimeters. And over here, that would give me 133 centimeters. And 95% is within 2 standard deviations of the mean. And so I have 68% within 1. So that leaves what? 27. 95 minus 68 is 27. And again, since it's symmetrical, that means I've got 13.5% here and 13.5% here. And we're going to go out 1 more. Let me extend this just a little bit. So let's say we've got 3 standard deviations. and -3. And so I'm going to add 8 to 165. So that would give me 173. And this would give me 125. Okay, and so there is 99.7% within 3 standard deviations. And so this will make this right here 2.35%. And this 2.35. And then greater than 3 standard deviations. It's 99.7. So there's 0.3 outside of 3 standard deviations. And so that would be 0.15% greater than 3 standard deviations and 0.15% less than. And so now let's answer the questions. And this is heights 12-year-old boys. Using the above sketch, about what percentage of 12-year-old boys will be over 157 centimeters tall? So 157 falls at 1 standard deviation above the mean. So below the mean would be 50%. And then I'm going to add 34% because it's 1 standard deviation above the mean. So that gives me 84%. So 100 minus 84. About 16% of the 12-year-old boys will be taller than 157 centimeters. And about what percentage of 12-year-old boys will be between 133 and 144? I labeled that right there, and it's 13.5%. So there's about 13.5% between -2 standard deviations and -1 standard deviations of the mean. And so if you were asked to sketch a normal distribution, it would look something like this, okay, with the mean and the standard deviations and everything labeled. And for shorthand, kind of the shorthand notation to write a normal distribution, I would do N, and then the mean would be 149, and the standard deviation is 8. And then it's good practice to label those two things. So that is mu, and that is sigma. Questions for me up to now? There we go. Back at it. It says, suppose that a distribution of test scores is approximately normal and the middle 95% of scores are between 72 and 84. What are the mean and standard deviation of this distribution? So if we draw a quick sketch of a normal distribution, I've got the mean, I've got 1 sigma, then I've got 2 sigma, -1 sigma, -2 sigma. It says the middle 95% of the scores are between 72 and 84. That means that 72 is going to fall at -2 sigma. And 84 will fall at +2 sigma. So 72 to 84, that's a width of 12. And there are 1, 2, 3, 4 standard deviations from the lower bound to the upper bound here that was given to us. And so that means that the standard deviation is 3. 12 divided by 4. And so that's going to make this 75. The mean would be 78. And this would be 81. So if I were writing this, I've got a normal distribution. the mean is 78. And standard deviation is 3. And then label it. So, we have what is called the standard normal distribution. And the standard normal distribution has a mean of 0 and a standard deviation of 1. It is the standard normal distribution, and it corresponds to what we did in the last section, which is a z-score. So a z-score is defined as the observation x minus mu over the standard deviation. And so we're going to look at several examples here. It says find the proportion of observations from the standard normal distributions that are less than 0.54. And so I'm going to do this for the first one, but I don't think you have to do this for all of them, but I'm going to make a quick sketch. Okay, so if I have a standard normal distribution here, this is mu. This is 1 sigma, this is -1 sigma. Then they are asking, if I go to 0.54, this is saying that it is 0.54 standard deviations above the mean. It is positive. And so we want to look at what proportion of the observations are less than 0.54. Standard deviations above the mean. So I'm going to introduce you to your new stats friend, normal CDF. Okay, so normal CDF. It stands for cumulative distribution function. So normal CDF. And so the notation for normal CDF is going to be the lower bound, then the upper bound, and then mu and sigma. So in this case, we're going less than 0.54, everything less than 0.54. So the lower bound would be -infinity. The upper bound would be this value, this z-score, 0.54. And then mu and sigma are standardized. So mu would be 0. And standard deviation would be 1. And then I want you to do one other thing for me, okay? So let's talk about like 2 scenarios. First scenario, it's multiple choice on the AP exam. Then I don't care, just get the right answer, okay? If it is free response, however, sometimes they can be picky about the notation. Okay, and so I want you to label what these things are. All right, so this would be lower bound. 0.54 would be upper bound. And I think you can abbreviate there. Mu would be right there. And sigma would be right there. And then we're going to use our calculator to calculate it. So let's do that. So go to the scratch pad on your calculator, and the scratch pad is right here between escape and tab. So from the scratch pad, I'm going to go to menu. And then statistics. And then I want to go down to option number 5, which is distributions. And then I want to choose option 2, which is normal CDF. And then it's going to prompt you for those values. So the lower bound was -infinity. The upper bound in this case was 0.54. Make sure you get the decimal there. 0.54. And then the standardized default is going to be mu of 0 and sigma of 1. So I'm going to hit OK. And then it tells me 0.705. So let me go back to the notes here for just a second. So this is saying that the proportion of observations that are less than 0.54 standard deviations above the mean is approximately 70.5%. Okay, and look at our little sketch there. Does that seem like a reasonable answer? Sure. Okay, let's do another one. This says greater than 3.89. So I'm going to do normal CDF. This time my lower bound is going to be the z-score 3.89. The upper bound would be positive infinity. And then we standardize, so mu and sigma are 0 and 1. And let's label it, okay? Lower bound, upper bound, mu, sigma. And so now take your calculator. And let me show you where positive infinity is. Okay, so again, I'm going to go to menu, statistics, distributions, normal CDF. And the lower bound here is 3.89. The upper bound is infinity. Okay, so infinity, if you will look right below the delete tab, there's a little book, and above the book are some mathematical symbols in blue. So I'm going to hit Control and then the book right there. And that will give me all of these mathematical symbols, and infinity is right there. So I'm going to choose that. And what should my percentage be like? Is it a large number or a small number? It has to be a small number, right? Because we're almost 4 standard deviations above the mean, and it's asking for the proportion that is greater than that. So I'm going to hit OK. And yes, we get 0.00005 for that. So let me go back to my notes here and write that in. So this would be 0.00005. Okay, let me check your answers here. Okay, this one would be normal CDF greater than negative 1.12. So that's going to be negative 1.12 to positive infinity. And then mu and sigma are 0 and 1. Label. Okay. Lower bound, upper bound, mu and sigma. Okay, and so for this one, I got 0.869. Within 1.5 standard deviations of the mean. So that would be normal CDF. We're going to go negative 1.5 and then positive 1.5 to get within 1 standard deviations of the mean. And then mu and sigma are always 0 and 1 when we standardize. So lower bound, upper bound, mu, sigma. Label it, and I got 0.866. And then for this one, we've got normal CDF 0.49, 1.82, 0 and 1. Lower bound, upper bound, mu and sigma. And I got 0.278. Yes,
Did we write those out as a percentage, or do we just keep it as?
that's fine if that's what they asked for. Within the context of a free response question, you might have to write it out, but we'll look at that in a second. Okay, and as I said, if you're using the TI 84s, will do these. Okay, you have to go to distribution and then normal CDF, but the notation, we do 1E99 is positive infinity for the TI 84s, and negative 1E to the 99 is going to be negative infinity for that. You're using an 84. Okay, so we are going to look at two more quick examples here and then finish this up for tomorrow. So let's look at that. It says in the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his first serve speeds is normal with a mean of 115 and a standard deviation of 6. All right, so I would write it like this: normal distribution. Mu is 115. Sigma is 6. And part A says, about what proportion of his first serves would you expect to be slower than 103 miles per hour? So if I make a quick little sketch, this would be 115. 103 would be below the mean. And I'm looking at the proportion that is slower than that. And so write it like this. I want the probability that X is less than 103. And you must standardize, and you must show the Z-score for full credit. Show the Z-score. Okay? Yes, your calculator will do it for you, but you don't get credit for calculator notation on the AP exam. So show your Z-score. All right, so my value X is going to be 103 in this case, minus the mean, which is 115, divided by the standard deviation, which is 6. I don't even need a calculator, right? So that's -2. And so I want the probability that my Z-score is less than -2. And so I'm going to put that into normal CDF. So normal CDF, we want our lower bound to be negative infinity, our upper bound to be -2, mu and sigma are 0 and 1. Lower bound, upper bound, mu, sigma. So take your calculator and put that into normal CDF. And somebody help me out. What percentage is that? Okay. And so now is when I would write my conclusion in context. If this were an FRQ, so I'm going to say about 2% of the first serves are slower than 103 miles per hour. And so last one here, B says, about what proportion of his first serves would you expect to exceed 120 miles per hour? So we want the probability that X is greater than 120 this time. Find the Z-score. So Z is 120 minus 115. Divided by 6. That's gonna give me 5.6, which is 0.833. And so I want the probability that my Z-score is greater than 0.833, so normal CDF. We've got 0.833, and my upper bound is positive infinity. Mu and sigma are 0 and 1. And let me label those. Lower bound, upper bound, mu, sigma. Put that into your calculator. And I got 0.202. So about 20% will exceed 120 miles per hour.